Hi, and welcome to this video. In this video, we're going to be looking at the law of constant composition, empirical molecular formulas, and a couple of different ways to classify states of matter. First established by the French chemist Joseph Proust, the law of constant composition, sometimes called Proust's law, states that a given chemical compound always contains its component elements in a fixed ratio that does not depend on its source or its method of preparation. That is to say, wherever you find a compound, it's always going to have the same composition. I think we can summarize that by saying that a compound will always have the same ratio by mass of elements. Proust is a little bit near and dear to my heart because he did a lot of his work in Segovia, Spain, which is also where I studied abroad. Shown here is an obelisk in front of his research labs in Segovia. One good example of Proust's law is shown below. Two samples of carbon dioxide obtained from different sources are decomposed into the constituent elements, or the elements that make them up. One sample produces 4.8 grams of oxygen and 1.8 grams of carbon, while the other sample produces 17.1 grams of oxygen and 6.4 grams of carbon. And it turns out that if you do the math there, both of those samples come out with ratios of 2.7 masses of oxygen per mass of carbon, showing that it doesn't matter how much of the sample you have, but the ratios are the same. Now take a second and work through the second problem, the one shown below, looking at examples of carbon monoxide. Pause the video while you solve the problem. The next two terms I want to look at are empirical and molecular formulas. Empirical formulas are the ratio, or rather the simplest ratio, of elements in a compound. The molecular formula, on the other hand, is the actual formula of a compound. Below, we'll look at two different compounds and their empirical and molecular formulas, as well as some different ways to represent those compounds. First, we have methane, CH4. The molecular formula of methane is CH4. That's the actual composition of that compound. The empirical formula is also CH4, because there's not a simpler way to reduce that compound down. Shown here are a few different ways that we can represent that compound of methane. We can represent it with a structural formula, where we draw the atoms at right angles to one another. We can represent it with a ball and stick model, where we use balls and sticks to show the geometry. Or we can use a space-filling model, where we show the actual space-filling or volumes of these atoms. Next is acetic acid. Acetic acid has the formula CH3COOH. Here, the empirical formula can be written as CH2O. That is, if the molecular formula, I'm just going to write it slightly differently, C2H4O2, that can be reduced down to CH2O. Now, lots of different compounds have that same empirical formula, but only this acetic acid will have that molecular formula. The structural formula of acetic acid tells us why we write it the way we do. Something like that. A ball and stick model and a space-filling model is going to stretch my art. I'll attempt a ball and stick model. Something like that. And the space-filling model, you just have to use your imagination for that one. Actually, I take that back. I was able to get a space-filling model of acetic acid there. And again, you see some of the geometry that's conserved, and you get a good idea of the shape of that molecule. Shape is going to be a much more important topic later, but I think one important rule from now that we can keep in mind for later is that function follows form. That is to say, the shape of the molecule dictates the function of it. Next thing I want to look at here are a few different ways that we can observe matter. We can observe matter on a macroscopic level. This is water. We can observe it on a molecular level, or we can observe it on a symbolic level. And part of what we're working on here is being able to fluently move between those three. I think another example of that is shown in this graphic here, where we have observable descriptors, that is macroscopic or everyday experiences, which we can then write in symbolic form, including text, graphs, or formulas, or use some models or theories to explain what we're seeing. I think, again, being able to describe things in three different forms is valuable here. Moving along, we have a graphic organizer where we can categorize substances into several different groups. We begin at the top with pure substances, and from there can move into either elements or compounds. Remember from earlier that elements are the basic building blocks of matter, cannot be chemically broken down, or consist of just one kind of atom, whereas compounds consist of two or more kinds of atoms. Within the element category, we have single atoms, or we have molecules of atoms, such as something like maybe O2. We'll look at a few examples there. Here you see mercury, which exists as single mercury atoms, or here you have chlorine, which exists as two chlorines stuck together. If we consider compounds, we can divide compounds into either molecular or ionic compounds. Molecular compounds, otherwise known as molecules, or ionic compounds. A good example of a molecule is water, whereas a good example of an ionic compound is sodium chloride. We'll talk more about those later, but what I'd like you to focus on now is that ionic compounds are not molecules, so therefore the simplest ratio of an ionic compound is something called a formula unit. And it is a little bit of a sticking point, but I'd like you to remember the difference between a molecule, something that's an individual molecule that exists by itself, and a formula unit, which is just the simplest ratio of an ionic compound. Here we have carbon dioxide, an example of a molecule, and another picture of sodium chloride, an ionic compound. Notice the repeating structure of a formula unit, the repeating structure of an ionic compound. When we talk about ionic compounds, we're not talking about a single molecule or a single formula unit, but lots and lots of them repeating. One added complication here is trying to figure out which elements exist as molecules and which exist alone. One handy way to remember is that we have several diatomic molecules. These are atoms that exist as groups of two. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, when found alone, always exist as diatomic elements. In compounds, they can exist in other ratios, but alone, they exist like this. A handy mnemonic is Hofbrinkel for remembering these. Finally, take a minute and test yourself as you classify each of the following substances as an atomic element, molecular compound, or ionic compound. Pause the video for a second. There's some answers and explanations. Now take one more second and work on the Skill Builder 5.4 to classify the following five as their particular type of matter. Thanks for watching.